Welcome to the presentation of our work, N2F2, a method for hierarchical scene understanding using nested neural feature fields. The input to our method is a RGB video, which we use to create a 3D Gaussian splatting model of the scene. Given this 3D scene, we want to segment parts of the scene based on text queries. For example, given the query toy chair, the model should segment these two chairs. But we may also want to go deeper and segment more specific regions like the red toy chair or the green toy chair. We may also want to segment parts of objects such as the chair leg. Generally, scene understanding can be performed at multiple levels of abstraction. In this work, we explore semantic hierarchies and object relationships. To address this, we ask the question of whether language can be used as a tool for hierarchical scene understanding. Most methods for open vocabulary segmentation use CLIP to distill language awareness in 3D. However, CLIP can struggle with compositional queries. For example, for the query paper napkin, a CLIP-based model may detect paper and napkin as separate concepts. Most of these models are also inefficient. For example, LERF needs about 30 evaluations per given query, and this grows linearly with number of scales. The main idea in N2F2 is to encode these hierarchies into a single feature field, where increasing dimensions of the feature field encode finer granularities. We use physical scale as a proxy for these hierarchies, and physical scale is estimated to be the 3D size of an image segment. Furthermore, during inference time, we design a composite embedding that can aggregate information from all scales in a single forward pass, leading to efficient inference. Our architecture starts with a 3D Gaussian splatting model built from the input images. We use the segment anything model to extract segments from each input image and then estimate a physical scale for each of these segments. The physical scale is obtained as the largest eigenvalue of the covariance matrix of the projected 3D point positions. We model the feature field using a triplane representation, which we find to be more memory efficient than assigning a feature to every Gaussian. Finally, we propose hierarchical supervision as a training strategy. For every segment, the scale is used to pick a subset of features, which are then projected back to the original feature dimension, and then supervised with the CLIP features. This strategy distills information from multiple scales into the same feature field. We propose using a composite embedding for faster inference. This embedding is the weighted sum of all possible scale-aware features at a 3D point or pixel. The weights are query agnostic and capture the relevance of each scale to canonical phrases. Using this embedding leads to 30 times faster inference than LERF and 1.7 times faster inference than LangSplat. Now let's look at some results. This is a scene where we segment a cup, or we can segment the lid of this cup. We can perform a query lid of a box, which will give us the lid of these two boxes. Or donuts, or we can go more specifically to query chocolate donuts, or a blueberry donut. In a different scene, we could segment cookies, or we could segment the bag of cookies next to it. We can query stuffed, which will give us these two stuffed animals. Or if we say stuffed bear, it only gives us the stuffed bear. In summary, to capture different hierarchies in a scene, we propose the nested neural feature fields method. This leads to a better representation that can overcome the bag of words quality of CLIP-like encoders. Our proposed composite embedding strategy leads to significantly faster inference on any given query. That's all, and we look forward to seeing you at our poster 267 on Wednesday, 2nd October at 10:30 a.m. Thank you.